I already told you yesterday how important is this and how much is the division of this course with the differential calculus and integral calculus. So basically in this part of the course we will talk about integrals throughout the way. To build the concept of integrals, we will start with the area problems and distance problems. If you recall, when you started to talk about the derivatives, you started with velocity and tangent lines and those things for the differentiation. Here again you can see I'm talking about the distance, and you have already done this kind of questions in the differentiation part. The problem is that here we will talk about the distance in terms of the velocity when velocity is changing at every second. At that time, you know the formula of distance, calculating the distance. Distance is velocity into the time. This is the formula, velocity into the time to calculate the distance. But at that time, this thing was constant, means at whatever you were talking about, the velocity of that particle or the thing was supposed to be constant at every time. Now here we will see that velocity is changing. For example, a moving car. When you start the car, initially the speed is less and you want to change it. Sometimes you increase the speed, sometimes you decrease it. So every time, every second of the duration, the velocity is changing. So in that case comes the concept of this thing, that your graph is changing at every next moment. It's not a straight line. In the case of derivatives, it was a straight tangent line. Now in the case of integrals, we are actually struggling with this kind of fluctuation. Sometimes the value is smaller, sometimes it's bigger, sometimes again smaller, bigger, smaller, bigger. So variation. Similar is the case with the area. If you want to calculate the area of a triangle, you can see that all the three sides are connected. They are straight lines. All the three sides are straight lines. So there is a straight away formula that the area is half of the base into height, because all the sides are straight lines. But here we are trying to look into a situation where one side of the shape, whatever the figure is, one side of that figure is not a straight line. If you recall the yesterday talking, we said that for the parabola in the interval 0, 1, we are interested in this interval for this curve. The curve of a parabola looks like this. If this is your coordinate system, then the curve of parabola goes like this, both ways. But I am interested in this interval 0, 1, means I am interested to look from here up to here if this is 1. So we will try to find the area covered by this curve in this region. So the curve is going from here to here, and if the corresponding point of this one is here, this is 1, 1, then I am actually interested to find the area of this region. So this is my the region of interest. I don't care what is happening there. What's happening here, I don't care about it. So let me pick up this shape and remove all other stuff. So I'm going to pick up this shape for this curve function over this interval. And I'm interested to find the area bounded by that region. So the shape is like this. Now the problem is, if it would have been a simple triangle, that was so easy to calculate the area. Area equals to half of the base into height. Can you hear me?
I can hear you.
Okay. But the problem is here that this is a straight line, this is a straight line, but this one is not a straight line. So I am struggling with this line. So this is not a straight line. I'm not allowed to apply this formula. No. This is only for a rectangle when all the sides are straight. Here, a triangle. Here, this looks like a triangle, but this side of the triangle is not a straight line, it is a curve. So, I am interested to find the area of this region. Now, one thing. If you look at the coordinate system, the coordinates are like this. This is 0, this point is 1. Corresponding to this one, this point is, of course, 1, 1, and you know this. So if I connect this here, it seems like the area of this region will be contained within the area of a square box. So whatever the area of this region will be, it will be less than the area of this square box, and it will be greater than the area of the straight line. So our job is split this whole region into small regions, rectangular regions. So I'm going to split it 1, 2, 3. Initially we start with 4 slices. And I'm saying originally this whole shade was S. I'm saying now this is S1, this is S2, this is S3, this is S4. And the distance from 0 to this point actually was 1. Since I have divided this 1 into 4 parts, so now this is 1 by 4, this is 1 by 2, this is 3 by 4, and this is 1. So in between, now I have 4 intervals. The first interval is from 0 to 1 by 4. The second interval is from 1 by 4 to 1 by 2. The third interval is from 1 by 2 to 3 by 4. And the fourth interval is from 3 by 4 to 1. So actually, the big interval 0, 1, I have splitted this big interval into 4 sub-intervals. And for each interval has equal width. What is the width? The width is 1 by 4. 1 by 4 means 0.25. This is the fixed width of each interval. So this distance is fixed all the time. This distance, all these, this is 0.25, 0.25, 0.25, 0.25. So this distance is fixed. It means one side of the rectangle to me is sure that it is 0.25. Now, to find the area, now I am interested. I have separated the whole region into small rectangles. Although it doesn't look like a rectangle, but I am assuming that these are the rectangles. So I am interested to find the area of the rectangles separately. S1 separately, S2 separately, S3 separately, and S4 separately. So first I would like to find the area of S1, and I am assuming that S1 is a rectangle. Actually it is not a rectangle, it is still a shape like this, but I'm assuming it is a rectangle. Now if it is a rectangle, at this point it is 0, at this point it is 1/4. I have to look at, if I have 4 sides, if I look it from down, from this side to upward, what is this distance? This is 0.25. It means, what is the rule of a rectangle? A rule of a rectangle is that the adjacent sides will have the same width. This one will be the same, these two will be the same. So if I'm looking, I'm assuming this is a rectangle, then it means whatever width is this, the corresponding width will be the same. It will be 0.25, which actually doesn't exist, but I am assuming in my mind. Similarly, this is one point of looking at the rectangle. The other thing is, if I want to look at this rectangle from that side, then the adjacent side will have the same width, this side. So I am assuming if this width is what? The corresponding point, this point is 1/4 on the x-axis. When I put this value here into the function y, I get the corresponding value. Y equals to 1/4 whole square. This is what? This is this distance from here to here. Now there are two possibilities. Now let me show. I have a small paper and okay, let me make it look like okay. Can you hear me? Can you hear me? Now look. Now look at this shape. Okay. Yeah. Anyways, any part. I am assuming I'm standing here, and this is the shape. I am saying this is the side of the rectangle in front of me. Now I am looking at this rectangle. I don't know what is there. This is not visible to me. The only thing visible to me is this bar. Now I am looking from right to left. I don't know what is there, but I am saying that this is one side of the rectangle. Now if this is one side of the rectangle, then that is not visible to me, but according to the rule of the rectangle, the opposite side should have the same width, the same height. Do you understand?
Yes.
So it means whatever height is this, the opposite side has the same height, which is not visible to me. I'm just assuming. So that is the concept, that if I look from right to left, I will consider this size. Now the other concept we will talk later, that how it works from left to right. So far we are looking from right to left. So at every point here, all these you can split them separately. One is this, the next one is this, the next one is same like this, and so I have actually broken all these 4 into this. Now I want to look from the right. These two are the end points of each rectangle, and I am interested to look at them from these points, the right side. So what is this? This is 1/4, this is 1/2, this is 3/4, and this is 1. Okay? I don't care what is this. I am standing there and I am looking at this side, so I will assume that whatever this height is, the opposite height will be the same, which I don't know whether it exists or not, but I will assume according to the rule of the rectangle. So I will use these values to calculate the area. Now for the figure 1 S1, the formula says that you will multiply this side and this side for the area. Area of the rectangle is what? If this is rectangle and this is length, this is width, then the area is this side into this side, LW. So here for the S1, I am only considering this side of the rectangle and this side. This I know, all these bottoms are 0.25 fixed. So the bottom is 0.25 and this side is the square of this number because of this function, because this height will be calculated by that function. So whatever the value will be, you will put it into this function and you will get this whole length. So this number is 1 by 4. When you put it into this number, it becomes 1 by 4 square. So this is the area of the first slice. Similarly, the area of the second slice. Now forget about this and look at this. Stand here on the right side because we are considering from the right. So I am interested in this thing which is 0.25 and I am interested in this height which is according to this function square of this number. So it is 0.25 into 1 by 2 whole square. Similarly, area of S3 0.25. This width, this thing is same because we have separated the region equally, and that one is 3 by 4 whole square, and the area of S4, it is 0.25 into this number 1 whole square. So I only consider the right end points of the intervals 1 by 4, 1 by 2, 3 by 4 and 1. When I will get the value and I can say this is, let's say this is R4 because I have splitted the region into 4 slices. So I give the subscript 4 and I'm saying R4 for the right sided area of all the triangles. So R4 is sum of area of S1 plus area of S2 plus area of S3 plus area of S4. When you put all the values together, these values, this one, calculate this. When you put them together, the answer is 0.46875. This is the area of this whole shaded region when I am looking from the right side. Okay. Now, is it okay now? Zafar?
Yes. Yes.
Good. Now, so I have got one-sided answer. Now, we will carry on with the same slices, but this time, now I am interested to look at the rectangles from left sides. So I am only interested in the left points. For S1, the left end point is 0. For S2, the left end point is 1 by 4. For S3, the left end point is 1 by 2. For S4, the left end point is 3 by 4. I am not interested into the right end points. Now, again look at this figure. Now I am standing here and I want to look at the slices from this side. Forget about all those other slices. Only focus on this first slice. Now when I am standing here and I am assuming this is a rectangle and I am standing at this point. This is the total height. What is the height?
0.
0. When you put this 0 into this function, it will be 0. Y equals to 0 square
area.
0. So this height is, according to this function, 0. It means the height of this rectangle
has
whose
zero
width is
area.
whose width is 0.25. I know this width, but the height is 0. It means wherever it go, how much it go, I am assuming that the height will be, according to the rule of the rectangle, will be the same on both sides. If this side is 0, then that side is also 0. So this is a rectangular having 0 height
Zero area.
and 0.25 length. So this is a kind of a straight line. It is actually not a rectangle, the first slice, when I am looking at it from the left side. So
Right.
the area of S1 in this case will be the, of course this is the fixed value, the bottom is fixed, into the square of this number, which is 0. So the area of this, when I am looking at it from left, is 0. Now move to the second one, the area of S2. Now the second one is in front of me from this side, and I'm only looking at this side, this height. I'm not looking at this height, that is not visible to me. So I'm actually, in front of me, I have this height. And this height is what? This height is square of this number, because this point is 1/4.
Yeah.
And according to that function, it is y equals to 1/4 square. So this height is 1/4 square. And this height is visible to me. So I am assuming the other part of the rectangle, the other side of the rectangle will also have 1/4 square. So this is the number. The length, this is the same, 0.25 into this thing is 1/4 square. Similarly, area of S3 will be, this number is 0.25 and this side is 1/2 whole square. And area of S4, it is 0.25 and this number square, that is 3/4 whole square. Now when you add them together,
So Alicia is saying to reconnect.
now when you add them together, I will say that this is, if that was R4, then from left side I'm saying this is L4. And the answer for L4 is 0.21875. So when I was looking at the region from the left side, the area is calculated this. From the right side, the area is calculated this. Of course, this is the minimum value which an area can have, because I started from 0. And this is the maximum area this region can have, because I started from 1. From right, I started from the maximum point. From left, I started from the minimum point. So the area can only be possible between these two values. 0.46875, this could be the maximum value for the area of this region, and 0.21875, this can be the minimum value for the area of this region for this function only, for the parabola. So the area will be between this. Now
We cannot go the exact number.
no, because you are always assuming something here which is a margin.
Error.
Yeah, this is the error. But you can always get an efficiency. You will see in the machine they have calculated, like even for
Okay, the smaller we divide, the less error it
yeah.
has.
The smaller you will take these slices, the more accurate will be the area. That is why we always assume
Right.
that my h approaches to 0. What is this?
Okay.
This h is dx, del x.
Yeah.
What is this? This is this small region. So So whenever you will
Right.
take this infinitely many times smaller, the accuracy will be greater. So now this is for when we split this region into 4 slices. The same region, when they split it into 8 slices, and it means the del x is reduced. If this time the del x is 1 by 4, 0.25, if you split it into 8 slices, the del x will be 1 by 8, that is 0.125.
Yes.
So for this, they calculated these values, and the value here, this value is, this value is something 0.27, and this value is something 0.39, whatever. So you can see from right side it is 0.39, and from left side it is 0.27. So the numbers are approaching each other, means you are going closer to that specific number, which is actually the root. Do you remember the secant method?
Yes.
In the secant method, what we try to do, we try to approach that specific number which is a root of an equation, which is
From
the root
both
of an
sides.
equation from both sides, or from the right side or from the left side. We try to approach it. Same is the case here. From both sides, you are trying to approach that number which is the exact answer for the area of this region, but you can never find that exact number. You can get closer to it. And for when they split, now this is for the 8, and when they split this whole region into 100, when they took n equals to 100 on the computer and split this whole region into 100, means you are taking this distance 1 by 100, 0.01. When you take this distance like this, it means you will make 100 intervals. Now when you make 100 intervals, the accuracy is more closer, and the values, the right hand value is 0.3383, the left hand value is 0.3283. It means that if you now sum up this thing, you can say that yes, the area will be approximately somewhere 0.33.
Right.
So they are coming closer. When you take 1000, it comes more closer. In the
2 decimal.
fraction. So that's the procedure from left and right. The important thing is to understand what is happening from here, left to right, and the sides were important.
Right. Yes.
So now let us generalize the rule to calculate the area for this. When we say that, okay, if I divide this whole region into n intervals, I do not fix the
Okay.
I do not fix this number 0.25. I do not fix it. I say, okay, let me divide this whole region into n number of slices, infinitely many slices, n numbers. So it means what will be the each distance, what will be the each interval. The interval will be starting from 0, and the first one will be 1 by n, right? Then the second one will be from 1 by n to 2 by n, and so on up to n minus 1 by n to n by n, and n by n means 1. So you can only go between 0 and 1. That is, 1 is the final, this is the left. But actually you are dividing it into infinitely many, and I'm saying that suppose that is n. So it means now this, if I consider, now I'm again going to consider the right end points. Focus on the right end points of all these intervals. The right end points are these. So it means if I want to calculate the area of the each smaller region, then the area of S1 will be what is the total? The in between distance is 1 by n, because I have divided the whole region by this number. So the distance of the slices, the size of the delta x is actually is 1 by n. So for the first slice, the delta x is 1 by n. What will be the height? The height will be the square of the right end point according to this function, right?
Yes.
So it will be 1 by n square. Similarly, now this is the area of the slice 1. I have splitted the whole region into n slices. Similarly, the area of S2 will be,
Wait, can
this
you
is,
tell again this area?
look, this is the whole region. I am saying I split this whole region into n number of slices, which I don't know.
I get that,
Okay.
but S1.
Yeah. Now, these n number of regions will make these intervals starting from 0, and the first point is 1 by n, then 1 by n to 2 by n, 2 by n to 3 by n, 3 by n to 4 by n, so on up to 1. Now, area of the S1 is actually linked with this thing. This is slice 1.
Yes.
And I am considering the right end points. Means I am interested the right side of this slide.
1 by n.
The point is 1 by n. According to this function, the total height will be square of this number. So that is the height. And this is what? This is that 0.25. In that case, it was 0.25. Now it is 1 by n. Because I have divided whole 1 by n. So 1 by n into 1 by n is square.
I didn't get this point. Like how the width is 1 by n.
Because what is this? This whole
N.
region is 1.
Okay, 1.
Your interval is what? Interval is 0 to 1. So your initial point is 0, final point is 1. This is the big interval. I have divided this interval into whatever I am doing. When it was 4, I divided the 1 by 4.
Okay.
If I take 10, I will divide 1 by 10. If I take 100, I will divide 1 by 100. If I take n, I will divide 1 by n. So that 1 by n is the delta x of the slice. This one.
Okay.
And this guy is fixed.
Each part is width of 1 by n.
Yes. This guy is fixed for all the slices, 1 by n.
Right.
Similarly, area of the S2 will be, this is fixed, 1 by n.
1 by n.
But this guy will be
2 by n square.
Yes, 2 by n is square. Similarly, area of S3, 1 by n, 3 by n is square.
3 by n.
And so on. Now, what will be the total? The total will be, and when it was 4, I said it is R4. Now it is n, so I am saying it is Rn. And what was R4? It was area of S1 plus area of S2 plus area of S3 plus area of S4.
Yes.
Now it is Rn, so it means area of S1 plus area of S2 plus so on up to area of Sn, the nth slice. So the area of S1 was 1 by n into 1 by n square, right?
Okay.
Plus area of S2 was 1 by n
1
into
by n.
2 by n square. Plus if you want to write 3, you can write it. It is 1 by n into 3 by n square, and so on. So you can see the pattern.
1 by n. Last will be 1 by n.
It will be 1 by n into, let me write it n by n square.
Okay.
So it is 1. Actually it is 1. So you are writing it n.
Yes.
Now this is something important. In all this thing, if you take the bottom of if you look at this, you can take the bottom as common, and you can see the bottom is what? Everywhere the bottom is n into n square. N into n square.
Okay.
N into n square. n into n square. So it is common. You can take it out. N into n square means n cube. You are taking it as common. So the bottom is taken out. Only left is the upper things square. 1 square, 2 square, 3 square, n square. Okay? You have taken out all the bottom. When you open this square, it is n square into this n, it becomes n cube outside. N square into 1 this n cube outside. N into n square, n cube outside. So the bottom is taken outside as a common. Now the upper floor, 1 into 1 square, 1 into 2 square, 1 into 3 square, that is simply 1 square, 2 square, 3 square to n square. Is it okay?
Yes. Yes.
Good. Now this thing is already proved that the square of first n integers has a generalized formula, and that formula is, don't need to prove it. That formula is, I'm going to write it. That is a theorem already proven by somebody. And for this, the theorem says that sum of first n integers, what are these? These are integers. The square of, so these are the squares of first n integers. Square of first integer, square of second integer, square of third integer, square of nth integer. So all these are integers and they are squares. So sum of squares of first n integers is generally written as n into n plus 1 into 2n plus 1 divided by 6. This is a generalized formula for this. We're going to write it, and this thing was taken common. So I have got now this thing. Now
it's a new theorem, right? We haven't seen this before.
Yeah, this is already proven, and you don't need to go into the proof because it is a very lengthy.
We haven't studied, right? Okay.
Yeah, it is in the number theory. You don't need to, here we don't need to prove it. We are using it according to that theorem. If you want to prove it, you can check on internet, it proof is available. Anyways, now, so I have got this thing. Now I'm trying to apply the limit. I'm saying that when I take the number of intervals infinitely many, when I take n approaches infinity, means I am increasing the number of slices. What does this mean? If you increase the number of slices, the width of the delta x will decrease. If n approaches infinity, it means delta x approaches 0. Because when you split it into more slices, the delta x will keep on reducing. And if n goes to infinity, then what is the opposite of infinity?
Delta x is the width of one slice, right?
Yes. So when you split, okay, let me tell you again. When
so you are splitting in very small pieces that it's almost 0.
Yes.
Like you can
I'm saying that I am splitting the whole region into infinitely many intervals. When I say infinitely many, it means I'm taking very small delta x.
Yes, and that is almost 0.
Yeah, so I'm saying it is not exactly equal to 0. It is not exactly equal to infinity. In both cases, both guys are approaching to infinity and this guy is approaching to 0. So they are opposite to each other. When this guy approaches infinity, this approaches to 0. If this approaches infinity, this approaches 0. Means the very first big slice, when there is no sub-interval, it means the delta x is very large. So delta x is very large, n is very small. But when I split into many slices, n is very large, delta x becomes small. So they are opposite to each other. Anyway, so I'm assuming that when I take this n, the number of slices, infinitely many, so that I can apply the limit n approaches to infinity on this guy, Rn. So what does this mean? I can simply apply this limit on the right side. That is limit n approaches to infinity, 1 by n cube, n into n plus 1 into 2n plus 1 divided by 6. Now this n and 1 n from here cancel out. and the leftover is limit n approaches to infinity n plus 1 into 2n plus 1 divided by 6 and n square from here. 1n was cancelled with this, so left was n square. It is here. Now this 6 is a number, so this limit has nothing to do with the number. You can take it out. So 1 by 6 comes out. Limit n goes to infinity. Now you can do the manipulation here. You can write them separately. N plus 1 divided by n square. Right? You can take 1 and another common. Yes. Can you simplify this? Have you solved this before?
I guess.
Okay. N plus 1 into 2n plus 1 divided by n square. Now try to simplify this. Split them and try to simplify what will be the answer. You have done it in the first chapter already. This limit, you have solved it. I have it on my paper, but I'll tell you first. You to do it because you did it already. Happening something?
Can we direct apply a limit?
No. If you directly apply the limit, it will become infinity.
Oh, no.
It will become infinity. That's not possible. You have to do something.
We can separately apply on each.
How? If you separately apply, what will happen? For example, if you apply a limit on this guy, n square separately, it will become infinity by infinity. That is not a good thing. We are not allowed. You simply have to do some kind of manipulation. Okay, let me do it for you. The manipulation is coming here. It is 1 by 6 limit n goes to infinity. These are n square, means it is n dot n, right?
Okay.
I can write it like this.
Yes.
So I am picking up one n with this, n plus 1 divided by n, and I am taking the other n with this guy, 2n plus 1 divided by n. Still it is the same, just I have separated them like this. Now if you do the division, it will become 1 by 6 limit n goes to infinity, n divided by n, it will become 1 plus 1 divided by n. You are dividing this thing separately by this.
Okay. Yes.
Similarly here, 2n divided by n, it will become 2 plus 1 divided by n. Now this is the rule. When you know this thing, that when you are trying to apply a limit, try to make an expression like this, such that n should be on the bottom if the limit is approaching infinity. Because when you will divide a number with infinity, it will become 0. So now you are able to apply this limit directly. You can replace the values of n with infinity. So it will become 1 by 6 into 1 plus, now I am just applying the limit, 1 by infinity, 2 plus 1 by infinity. This guy is 0, this guy is 0, because a number divided by infinity is always 0. So it is 1 by 6 into 2, that is 1 by 3. So this is the area of that region built by this function over this interval. 1 by 3 is actually the area of that region. But again, this guy shows that this is an approximation. So it is not an exact answer. So you can say that area of the region S is approximately
approximately
1
1
by
by
3.
3. Because it's not exactly infinity, it's
Because this is approaching infinity. So if this is
Yeah.
approaching infinity, everything is approaching, not exactly.
approaching.
So this means that it approaches 1 by 3, but not exactly 1 by 3.
Everything is lie in mathematics.
No, it's not a lie. It's actually, we are trying to go closer to the nature.
Yeah.
So everything, actually whatever is working, it is working on approximation. Whatever you are doing,
Yes,
everything,
exactly. That's
they
what
have a
I was
margin of
thinking.
error. Everything, they have some margin of error.
Alright.
Now, this whole thing I have done using the right endpoints. Now the task is do the same thing but use the left endpoints. Can you do?
It will be the same method, right?
Answer
But
should be
just
the
we
same
have
method.
to assume the
Answer will be the
left.
same. Answer will be the same.
Okay.
Ln. The answer will be 1 by 3. But this time you have to consider those intervals.
Only the
Okay,
left,
let me tell you.
left sides.
Let me tell you what will be the points. The width will be 1 by n, that is for sure.
Yes.
But
Yes.
the intervals will be 1 by n, then 1 by n to 2 by n, and so on up to n minus 1 by n and n by n. Now you have to pick up these guys. Then from the next it will be 2 by n, and this from the final you will pick up this, not this. I pick up the right points. This
Right.
guy, this
Yes.
guy, and this guy. Now you have to pick up left guys. This guy, this, and this one. And just try to simplify the expression, that what will be the final expression. And if you can apply the limit on it, apply it. Or if you are unable to apply the limit, just give me the final expression. What is it? So I will see you after the break with that expression.